Discrete Fourier transform. In the chapter, we'll discuss about computations in DFT. Discuss scaling and linearity property, periodicity property, time shift property, and frequency property. Scaling and linearity property. DFT of x of a times x1 of n plus b times x2 of n is a times x1 of k plus b times x2 of k. When input is scaled, corresponding output is also scaled. When inputs are added, output is also added. When inputs are scaled and added, output is also scaled and added. This is called scaling and linearity property. So let's take one example of x of n equal to 1, 2, 3, 4. To find this x of k, first we'll write DFT formula, then matrix representation of DFT equation, matrix substitution, then matrix multiplication, and we'll get this answer x of k. P of n is 2 times delta n plus x of n, and we want to find P of k using x of k. To find P of k using x of k, first we have to write P of n in terms of x of n, which is ready-made given here. Apply DFT property. By applying linearity property of DFT, we get P of k equal to 2 times DFT of delta n plus DFT of x of n. DFT of delta n is always 1, so 2 into 1, and DFT of x of n is x of k. So P of k is 2 plus x of k. This equation we have to evaluate for every value of k. Here x of k is 10 minus 2 plus 2j minus 2 minus 2 minus 2j. So let's put k equal to 0. We'll get P of 0, that is equal to 2 plus x of 0. X of k is 10. Similarly, k equal to 1, P of 1, 2 plus x of 1, P of 2, and P of 3. Now here we'll have to replace this x of 0 by 10. 2 plus 10, 12. X of 1 is minus 2 plus 2j. 2 plus minus 2 plus 2j is 2j. And so on. This is P of k. Now Q of n equal to 2 plus x of n, and now we have to find Q of k using x of k. To find this Q of k using x of k, we have to write Q of n in terms of x of n, which is given here. Now we have to decide which property we can apply. We can apply linearity property. But linearity properties can be applied only when signals are added. If this is x of n, then this should be dependent on the variable n. Signal, it should be dependent on n. There has to be variable term like n, but here I don't find any variable term like n. We have to add variable term here. So for that, let's do some little manipulation. 2 is multiplied by 1 plus x of 1, and this 1 is nothing but u of n, but u of n is infinite length signal, so we cannot find DFT of infinite length signal. We know that x of n is 4-point sequence, so we'll assume that q of n is also 4-point sequence. So we will also assume that u of n is also 4-point sequence. So for 4-point sequence u of n, DFT is 4 into delta k. 4 into delta k means 1000, and x of k we have already calculated. Addition of this, by simplifying, we get this answer. 4 into 2, 8, into delta k is this, same as delta n, x of k is this. This is the answer. According to periodicity property, both the DFT and IDFT equation produce periodic result. That means x of k is periodic because of DFT equation, and x of n is periodic because of IDFT equation. If x of n is periodic, then x of n equal to x of n plus n. If x of k is periodic, then x of k equal to x of k plus n. This can also be written as x of n mod n, valid only for periodic signal. X of circularly shifting of n. Circular shifting is only for periodic signal. This is valid for frequency domain representation of the x of k. So DFT produces periodic result, that means x of k is periodic. IDFT equation produces periodic result, that means x of n is periodic. Next property, time shift property. According to this property, DFT of x of n minus m is wn raised to mk x of k. X of n minus m means x of n shifted by m. X of n is defined in time domain, that means there is a shift in time domain. Therefore, it is called time shift property. In frequency property, x of k is shifted. So DFT of wn raised to minus m in x of n is x of k minus m. Here x of k is shifted, here x of n is shifted. So let's take one example. X of n is 1, 2, 3, 4. We know this x of k. Now we want to find out p of k using x of k. P of n is given, but equation of p of n in terms of x of n is not given. Instead of that, p of n values are given. So let's compare these two signal values. 1 shifted, 2 shifted, 3 shifted, 4 circularly shifted. So every signal value of x of n is shifted here in p of n, right side by 1. So we can write p of n equal to x of n minus 1. And then we can apply time shift property. So DFT of x of n minus 1 would be wn raised to k x of k. Now this equation we have to evaluate for every value of k. When k is 0, wn raised to 0, x of 0. K is 1, wn raised to 1, x of 1. K is 2, wn raised to 2, x of 2, and so on. Wn term will get from circle diagram. X of k we already calculated. Multiply 1 by 1, you'll get p of k, answer. P of n equal to minus 1 raised to n x of n, and we have to find p of k using x of k. To find p of k using x of k, we have to write p of n in terms of x of n, which is ready-made given here. Let's find out what is this parameter. Here x of n is multiplied by something. That something is not constant. If this is constant, we could have applied scaling property. Instead of that, this is variable term because there is a varying parameter like n. Whenever it is a variable, this we have to apply frequency property. Frequency property we can apply, but according to the property, x of n is multiplied by w term. So this minus 1 will have to replace it by the appropriate value of Friedel factor. We know that for n equal to 4, wn raised to 2 is minus 1. So this minus 1 will get replaced by wn raised to 2. P of n is wn raised to 2n x of n. By frequency property, P of k is x of k plus 2. Now we have to evaluate this equation of P of k for every value of k to calculate the values of P of k. Put k equal to 0, you will get P of 0, that is x of 2, x of 2 is minus 2. Put k equal to 1, that is P of 1, x of 1 plus 2, that is 3, x of 3 is minus 2g, and so on. So we have to evaluate this equation for every value of k and obtain this required value of P of k. X of n is given 1, 2, 3, 4. Find the inverse DFT of the following sequence without using DFT and IDFT equations. That means we'll have to use only properties. To find inverse DFT of x of k minus 2. To find inverse DFT of x of k minus 2, let's say P of k is x of k minus 2. Here we know that x of k is shifted. That means you have to apply frequency property. So by frequency property of IDFT, P of k ka IDFT P of n, and IDFT of this is wn raised to minus 2n x of n, because we know that DFT of this is x of k minus 2. And wn raised to minus 2 is minus 1. So by evaluating this equation, we can get the required values of P of n. Put n equal to 0, n equal to 1, n equal to 2, and so on. Similarly, to find inverse DFT of x of k plus 2, let's say P of k is x of k plus 2. By frequency property, P of n will be Wn raised to 2n x of n, but Wn raised to 2 is also minus 1. That means in this case we'll get the same answer.
Coursera is an online learning platform designed to provide high quality structured education in a flexible and accessible way. The platform offers academics and professional courses across science, technology, engineering, and management. Visit www.coursera.in. Midnight Masterclass is a YouTube channel, and we welcome you to Midnight Masterclass, your late night destination for learning that is actually fun.
Thank you.